All right, 27 and 28. Let's have a look at this question. All right, massive massive fuel cell here by the looks of it. I'm just going to go straight to the question and have a look at it. Main thing I care about with this is it's a fuel cell, and that we've got some equations here as to what's happening in this fuel cell / battery. All right, so question 27. The overall reaction that occurs when the battery is discharging, so that's when it's releasing energy, and this is going to be found using these two half equations here. So first thing I want to know is, are they in the right order? Because VCAA sometimes like to mess with your head and put the negative one above it, but they don't. This is in order as they would be on the electrochemical series. So this is going to react with this. So what we should see is the fact that VO2 would react with V2 positive. So VO2 and V2 positive, that looks good. So that's fine. VO, that's not going to be right. VO2 positive, that's not right, and VO plus, that's not going to be right. So it has to be A by the looks of it, just by knowing what's going to react here. If I wanted to go through it further, I'd make sure that the electrons are the same, which they are, and just add the two equations together. But initially, I just want to make sure that my reactants are correct. So therefore, A is the bang on right answer there. So even if we have all this preamble, don't need it much at all, to be fair. Just nice information. Go look at the question first and then come back to that information. Let's have a look at the next one. Question 28. If air is present, the following half equations are also relevant. So here's two more half equations. We can add those to our couple over here as well. What do we notice about these? I notice that this is now the strongest one, and this one's halfway between the two. Alrighty, so what's going to happen if air is present? What is our strongest, what's going to happen? So if air is present, this will no longer react because the O2 is a stronger oxidant. So therefore, it's actually going to be reduced. The oxygen is going to be reduced. But the V3 positive, so the V2 positive is still the strongest reductant. So that's not going to happen. So let's see, the strongest. This is oxidized to that. That's not going to happen. Alrighty. VO2 positive is reduced. No, that is not the strongest oxidant, so that's not right. V2 is oxidized to VO2 positive. So if that is reacting to that, well, I don't think that's right either. VO2 positive is reduced to VO2 positive. That's, what is happening here? If air is present, let's have a look. This is going to react. I need to work out what's going to happen here, actually. VO2, V2 positive. The V2 positive is good. Alrighty, we don't say this is recharging. So let's have a look. VO2 positive. Why would we have that reacting at all? If air is present, we've got that is going to react with that. Okay. That reacts, that's formed. Oxygen reacts, that's formed. I think I know what's going to happen. Alrighty, so this is going to react and form the V3 positive ion, and that V3 positive ion is going to be here. Alrighty, and then this here, this ion is going to react and form this here. So as a flow-on effect, C is going to happen. Alright, definitely not D, but C is going to happen because oxygen's strongest oxidant, V2 positive, is the strongest reductant, which produces V3 positive. And then once all the V2 positive is used up, V3 positive becomes our strongest reductant, and then it's oxidized to form that. So answer will be C. Let's move on. It took a bit of time. The following energy profile shows the results obtained from an enzyme catalyst reaction. Each stage is labeled M blah 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 blah. N is the enzyme complex, I'm guessing. The stable intermediate. P represents the final products. from which of these following statements is correct? We're basically looking to see if they're endothermic or exothermic. So the change from M to N, this is endothermic, so it's certainly not going to be A and B because M to N is endothermic, M to N is endothermic. That's what we want. And then the transition from N to P, that's exothermic. Alrighty, so I've already crossed out A, so it's not that one, it's not B. So energy change from N to P is endothermic, N to P, that is not right, so it has to be D. Let's just double check it. The energy change from M to P is endothermic, so going from here, going up to here, that is correct, so that's all good. Main thing is we have this here is endo and this here is exo. So that's all we're going to be looking at for that one. That's 29. Last question on our multiple choice. The diagram below shows a basic setup for an electroplating cell. So we're trying to make metals grow by chucking electricity into them. Initially, the cell was set up with lead at electrode Z and lead nitrate there. As the electroplating solution, the cell runs for a set period of time. We get 1 gram of lead produced. 4 subsequent electroplating cells are set up, each containing a platinum electrode and a different electrode Z. That sounds good. The appropriate electroplating solution, 4 of these cells are operating at the same time at the same current as the original P electroplating cell. Which combination of electrode Z and electroplating solution would produce more metal? So what we want to see is, are we going to produce more than 1 gram of lead here? So which one's going to produce the most by mass onto electrode Z than the original P plating electrode? So let's have a look at initially, basically what we're going to look at is, are we going to produce more mole? Well, which ones of these are going to produce a reasonable amount of mole here? Because that's going to help with this. This is a Cr3 positive ion, this is an Ag positive ion, this is an Au3 positive ion, and this is... Oh, phone ran out of space, but now I'm back. So let's have a look at this. What did I get to? I was talking about this. Gold is 3 positive, tin is 2 positive, and our lead over here is also 2 positive. What does that mean? Well, that means that based on these charges is how many electrons each of these things are going to get. So therefore, let's first of all work out how many electrons we're going to have with our lead. I'll go get my molar mass of lead, which is on here. So lead is sitting around about here, which is 207.2. So 1 divided by 207.2 gives me how much mole of lead there was. So that's how much mole of lead there is. There'll be twice as many electrons because it's a 2 positive charge. So therefore, the electrons are going to be equal to 0.0097, for example, of mole of electrons. So what does that mean? That means that I can look at that and say, right, take away 1, that gives me my number here. So the tin is going to have 0.0097 mole of electrons as well. My gold here is, well, my gold and my chromium are going to have the same amount, and that's going to be, what's that? 2 positive, so therefore divide by 2 times by 3, it's going to give me 0.01448, 0.01448 mole of electrons, mole of electrons, and divide by 3 times by 2, going back to the original thing. Silver will be half as many electrons. Stuffing this up. Never mind this. Let's go back to what I'm looking at. We want to look at mole of the actual stuff. So what was it? 1 divided by 207.2. All right. So what I'm looking at is the mole of lead. Mole of lead is 0.0048. Okay, that's how many mole of lead I'm going to have. Now the charge here is the same, so I'm going to have the same number of mole of tin. All right, the charge of silver is half as much, so I'm going to have twice as much silver produced. This makes more sense to me. 9, 6, 5. And my, what are they called? Chromium and my gold are going to have slightly less. So therefore, how am I going to do this? Well, I've got that much silver is being produced. It will be a third the amount of silver because of the charges. These charges are 3, whereas this is 1. So therefore, these guys need 3 times as many electrons to make a mole. So therefore, divide by 3, I'm going to end up with 0.0031 mole of each of these metals. This is probably the long way of going about it, but anyway, this is how many mole of these metals I'm going to have based on the ratio to my charge of my lead here. Now, I need to work out which one's going to have more mass than the original lead. I'm going to start off by thinking, well, this one's got the most mole, so it's probably going to be this one here. So I'm going to start off by looking to see if this is actually going to produce more mass. So I get my mole, I'm going to times that by molar mass, which I believe silver is 107.9, and it looks like it's going to be more than 107.9 gives me 104. So that is correct there. It gives me more than 1 gram of lead, because you can see, well, just by looking at it, this is going to produce more mole of stuff. And the main thing is we want to see the ratio of mole to the charge. Realistically, that's kind of, and the molar mass, I guess, in there. Just for kicks, let's just have a look at some of these other ones. The chromium molar mass is 52, so that times 52 is definitely going to be lower. The molar mass of gold is 197. If you think about it, this is a third of that, and it's timesing by less than half. Sorry, just less than double of that, so therefore it's going to be smaller. And the molar mass of tin, I'm pretty sure it's under 100 as well, so it's going to be pretty small. And tin is there, it's 118, sorry, 118. But yeah, definitely going to be smaller than the original one there. So B is our answer. There's probably a quicker way of doing that question, but oh well. That's how I did it. Hopefully that makes sense to you. If it doesn't, let me know and I'll try and do a better job of explaining it at some stage.